Hello. So, in this video, we are going to be tackling sort of the special issues that are around even roots, and in particular, simplifying roots that are sort of even valued. So, when we're looking at sort of odd and even radicals, the underlying reason that most of the time we sort of split these things apart, meaning like most of the reason why these things behave sort of very differently from one another, it usually revolves around the idea of negative numbers and really what's happening when we sort of inject negative numbers into this situation. So to explore that, let's look at two functions. So let's just take sort of a basic even, so x squared, and a basic sort of odd that isn't trivial. So we're going to look at x cubed. So looking at these things, radicals are sort of designed to undo exponents, but let's sort of look at what happens in the forward direction first, meaning let's see how f and g, how they treat -1. So in particular, if I look at g of x, right, g of x is x cubed. So if I want to evaluate -1, I plug in -1 cubed, that's -1, right? And sort of obviously, right, if I plugged in a +1 cubed is also +1. So when I take an odd exponent, well, when I do it to a negative value, I get a negative. And at the same time, if I do it to positive values, I get positives, meaning that it sort of preserves the sign, or what we say in this case is that it's preserving the negative, right? The negative stays, positive stays, so it doesn't change the sign. Now, in contrast, if we look at x squared, well, plugging in -1 squared is 1, right? Already we've lost the negative. So even exponents, we say it would annihilate the negative. It gets rid of the negatives. So in particular, when we're using even exponents, we only get positive values. So this is the like anything squared is not negative, right? Or typically people say anything squared is positive, which is almost true, right? 0 kind of screws with that. But point is that you never get anything negative, at least for real numbers. So since there's no real number that sort of works, right? There's no something squared equals -1. Well, that's sort of the underlying problem in comparison with g of x, right? So if I look at g of x and I say, okay, what if g of x, I just know that g of x equals 1. I want to know what the x is, right? So now I'm trying to go backward, which is where the radicals come from. So if I cube root both sides, well, on the left, I just get x. On the right, I get 1. And that works because g of x preserves negatives and preserves positives, so I know that it sort of has to be that one value. Now, in contrast, if I look at x squared, right, and I say, okay, well, where is x squared equal to 1? Well, I can still undo the square. That gets me a square root, and the square root is 1, but not quite, right? Because if I think about it, well, if I plug in -1 squared is also +1. So really there's two answers here, but my square root only gives me one answer, right? Because square roots have to be a function, so the square root itself only gives the positive, and there's something sort of mysterious or shady going on here that I only got one of the two answers. And that's because what we did on the right is actually not correct. That's what we're trying to tackle is why is this wrong? Why am I getting x equals 1? And like, how do I account for the fact that -1 is also an answer? So the sort of underlying problem here, right, is that even exponents annihilate negatives, and that means that if I'm looking at an even-powered thing, like x squared, then if a positive works, the negative also works, right? So if 4 were an answer, -4 would also be an answer if I'm just looking at something squared, because the squared doesn't sort of differentiate between the two. It annihilates the negative and ends up making the thing positive regardless of the input, okay? So this is the sort of thing that we're trying to tackle. That's the underlying problem that we're trying to deal with in this video. All right. So since even roots, they can't distinguish between positive and negatives, we need some way of representing that fact, right? In some way, these roots are sort of converting everything to a positive thing. But to accomplish this, we can use sort of another function that does the same thing, right? Another function that just takes whatever it is, whether it's positive or negative, and forces it to become positive. that's absolute values, right? So we can get around this problem. We have to be a little clever, which we'll talk about in a second, but we can get around this using absolute values. But there's an asterisk on that too, because of course, right, math. and the reality is that the thing is that as we go forward in math, we'll find that absolute value functions are just really annoying to deal with. And in fact, whenever we can get away from not using them, we try really hard to get away from that because they have sort of very unfortunate properties. Moving forward, if you're going into calculus, absolute value is one of those classic examples where we have something that is continuous but not differentiable. And so you sort of are looking at something that is not smooth in some sense. If you're not following that, don't worry about it. It isn't important for this class, but I'm just saying this motivates why, sort of as math people, we really don't like absolute value if we can get away from it. So absolute values tend to generate just considerable headaches in a lot of different sort of real life settings like physics and things like that. And so what we really want to do is sort of find a balance, because on the one hand, we have to use absolute values because they're the sort of analog for this even root problem that we're dealing with. So they're sort of the way that we solve our issue of missing answers. But on the other hand, we sort of want to not use absolute values as much as possible because they actually generate sort of all kinds of headaches all on their own for other reasons. So we have this balancing act to do where we want to get all the solutions while using as few absolute values as we possibly can. So how do we do that? Well, let's go through it. So let's say we have this radical to solve. Now, if you remember from the other video or other sources, simplifying this radical, we have sort of a process, right? So the first step, we want to make sure that the thing is factored fully or factor it if it isn't. Here, we have a nice fully factored one. So step one, done. Good. Step two, we split each of these factors into two parts, right? The largest multiple of the root values. The root value here is 2. So I want to split each thing up into the power that is the sort of largest multiple of 2 that doesn't, go past it, and then the remainder bit. So we have, right, the purple is the largest multiple, the green is the remainder. So if I look at my thing, right, my expression here, I can say, okay, for example, x to the 5th, that's x to the 4th, that's the highest multiple of 2 power. And then I have x to the 1 over here, that's the remainder bit. And we do that for each of these, right? So x minus 3 squared, that has itself, right, x minus 3 squared is the largest multiple of 2 power, and there's no remainder because I used them all. So it's not over here in the green. Go through each of them. So far, it's the same as the odd sort of radical situation. So it's the sort of same process so far. The next step, well, this is where we do something slightly different for even. Almost. So step 3 is, for both of them, step 3 is pulling out that first group and dividing each of the exponents by the root value. But when we do that with an even root, we have one extra piece on top of that, which is that everything we pull out gets an absolute value. Now, I know I said, like, oh, it's not as simple as just throwing absolute values on everything, which is true because there is going to be a follow-up step that is only for this situation. But initially, everything gets an absolute value. That's sort of your safest bet. So taking this piece here, right, we're looking at this first bit where I have x to the 4th, x minus 3 squared, x plus 1 to the 6th, x plus 7 to the 8th. All of these, right, I pull out and I divide by the root value, which is 2, and I put absolute values around all of that. So here I'm going to get absolute value of, right, x to the 4th, that 4 divided by 2 gets me x squared, right, and so on. And then the remainder stays inside. So when it's an even root, not odd roots, right, because odd roots are fine. They play nice with things, right? They preserve negatives. But with even roots, when I pull stuff out, I have to put everything in absolute values. But again, we don't like absolute values. So the next step is that we want to try to sort of justify getting rid of the absolute values anywhere we can. So what we want to look at is, okay, we've sort of have the radical, we broke it up, and then we pulled out the pieces we can pull out. We put absolute values around everything. Now, is there anything in here that I could sort of justify not needing an absolute value? For example, if I look at x squared, well, x squared is itself an even power. And we just said, right, that when I put in a negative, it gets rid of it. The whole point of using absolute value is that it behaves like an even power as well, right? So that means that if I'm looking at absolute value of x squared, that's redundant because the x squared part's already making it positive, or it's 0, but either way it's not negative. So taking the absolute value of a thing that's never negative doesn't do anything. So I can get rid of the absolute value around x squared because x squared is not going to ever need it, right? It's already positive. So if I do that sort of term by term, I can see that really the x squared term, right, that's an even power, so it's always fine. And this x plus 7 to the fourth, again, even power, so it's never going to be negative either. And so both of those, x squared and x plus 7 to the fourth, both of these pieces are going to be sort of always not negative, right? They're going to be 0 or positive, and so I can just take away the absolute value. They're not doing anything. But for the other terms, right, the x minus 3 to the 1 and x plus 1 to the 3, those are odds. They preserve negatives. They still need the absolute value. So this here is going to be my sort of fully factored result. And really, this sort of justification process is almost always because of exactly what we just said, which is that like almost always when you're removing it, it's because for some reason, usually because it has an even power, the thing inside has to be not negative already, and so the absolute value is not doing anything. That's what we want to think about. And as I said, most of the time, the lion's share of the time, this is because of the fact that we have a sort of even root already, like an even power. And so it's that even power is sort of doing that for us. But there are other situations like domain restrictions and stuff, if this is like a physics or real world problem where you have only certain x values you're considering, stuff like that. So wherever you can get rid of the absolute value, it's sort of a good idea to do so because absolute values are just really hard to deal with in most contexts. All right, so breaking this down into our sort of coherent strategy then for even or odd. Step 1, fully factor the radicand, right? Whether it's numeric or whether it's algebraic, always have to factor these things. Step 2, split each of these factors that's sort of inside the radicand, right, inside the root. We split it into 2 parts, the sort of perfect square, cube, whatever, right? The multiple that is the largest multiple of that root value without going over. So we have that part of it, and then we have whatever the remainder part is. And we do that for each term. Then step 3, well, we pull out the factors in that first group and divide each of those powers by that root value when we do it. And if the root power, right, the root value is even, only if it's even, then everything gets an absolute value that we pull out. But then the sort of next part of that is that we go back through and we try to justify what stuff we can pull the absolute values off of, right? So if it's like to an even power or there's domain restrictions or something, then we can remove the absolute values after that. Again, to be very clear, we don't have to do any of this stuff when it's odd because odds preserve the negative. So I just pull it out, divide by that root value for each of the powers, and I'm good. I'm done. It's great, right? Step 4. If we have numbers involved, right, if we have coefficients floating around, we want to multiply those back together so we just have the one coefficient instead of some crazy prime factor thing as our coefficient, because those are sort of obnoxious to do that with. But again, we don't do that with the algebraic part unless we have a really compelling reason to do so. All right, so what do we do? Well, we talked about the simplifying radicals again, but this time we sort of really focused in on how to deal with the even root values, right? And the fact that because evens annihilate negatives, they have to deal with this absolute value nonsense, where if we think of the case where we looked at x squared equals 1, if we square root both sides, I wouldn't get x equals 1, I get absolute value of x equals 1. And that's why we get x is plus or minus 1, because the absolute value of plus or minus 1 is 1, right? So these absolute values come into play when I'm looking at even roots. But at the same time, absolute values kind of suck. I don't want to deal with them. So I'm going to go through and try to remove them wherever I can sort of logically justify that it's not doing anything. Typically because the factor is still being raised to an even power even after I've sort of divided by that root value. Okay, so that is that.